All right, welcome back. Thank you for being on time, and thank you for being so well organized. It's so much fun to be in a country where people appreciate it much more, rather than having to shoo people in and say, like, don't stop shouting at each other. So, talking of people shouting at each other, I'm very happy to introduce Haris Pozidis here, or Haris Pozidis. Principal scientist and master inventor. That sounds like something from a Lego movie. This is pretty awesome. At IBM Research, and he's going to talk to us about SnapML and what that means. Please, you will know about. Again, Slido is open. Ask questions. He volunteered to answer questions afterwards. And yeah, don't feel bad that you're the one between them and lunch. No stress there. So let's hear all about SnapML.
Okay, so I guess you've seen here what is you've been asked a question in the beginning. What is your favorite machine learning framework? I guess most of the people answer TensorFlow. I'm disappointed. I only see 4% for SnapML. So I hope that by the end of this talk, this bar there for SnapML is going to rise all the way to the right. So SnapML is really another framework for machine learning. It is made today to work with classical machine learning, not so much for deep learning, as we will see a bit later. And its main claims are that it is very fast. For some reason, this doesn't work. How can I go to the next slide? OK. So it has three main characteristics. It's very high performance, as I will hope to show you. It can scale to very large data sets, talking about terabyte-scale data sets. I have an example. And it is very resource efficient. So why are these things important? Why is being fast important these days? Well, there are many cases where you need to respond to certain situations quickly, where sometimes the situation on which your previous model was trained have changed, and they change rapidly. And you may need to retrain your model very fast in order to adapt to these situations. Why do we need the model to be able to handle large-scale data? Well, typically these days, in particular with the rise of the internet-scale companies, we have data sets that are of very large scale, terabyte scale, billions of rows. And this typically comes in things like recommendation engines, credit card fraud for banks, online advertising. And I have an example, actually, from that later. And why is it important to be resource savvy? Well, not everyone today can afford to run a very large infrastructure, machine learning infrastructure on-prem. And typically, the small, medium enterprises, they run things on the cloud today. But running on the cloud means that you need to rent infrastructure. And when you rent infrastructure, you don't want to occupy this infrastructure for a long time, right? Because being a small enterprise, like a startup, for example, we have many here, you don't want to spend all of your money in renting machines in the cloud. So being fast, being able to run with a smaller number of resources is going to pay off in the end, in particular for startups and small enterprises. So what are, I forgot to say that Snap Machine Learning, or SnapML, is meant to train what we call generalized linear models, or GLMs for short. So what are GLMs? They're basically relatively simple machine learning models. They consist of either regression problems. For example, linear regression is a celebrated linear model. There is something else called lasso regression, which is basically a sparse version of linear regression. And on the other hand, we have, on the other side, we have classification. So support vector machines are a very popular model, which falls under this category, as well as logistic regression. Now, of course, these days, everybody talks about deep learning, about gradient boosting machines, about random forests, which are much more complex, non-linear models. So why are we talking about linear models here? Well, first of all, because linear models can give us what we wanted to do in the beginning, so can be trained very fast, because they do not have too many parameters, and the algorithms that are used to train them are simpler. Second, because, again, these models, they don't have too many parameters, or too many hyperparameters, as we call them, so therefore they need less tuning compared to the more complex models, like, for example, gradient boosting machines or neural networks. Another very important topic, especially in Europe, but all over the world, and we heard about this in the previous talks, is interpretability. And in particular, you're very well aware that in May this year, a new regulation called the General Data Protection Rule has come into force in Europe that basically gives the right to any EU citizen, which, by the way, may be a customer of any company across the world, not only in Europe, has the right to question or to obtain an explanation about any decision that is made of him. For example, a decision about his health, a decision about his credit score. So therefore, it is not only important, but it is paramount, it is necessary for a machine learning algorithm today and in the future to lead to an explanation of the decision that the algorithm has taken. And linear models are very good at that. They lead to natural explanations because they are linked to the features with linear weights. So therefore, by just looking at the weights, one can understand, actually it's a little bit more complicated than that, but one can understand which were the features in the data matrix that were most important in reaching a decision. And the last reason is actually that these models are still very widely used in industry. There is anecdotal evidence from many sides that today most banks and most telecommunication companies still use linear models, actually on a 90-10 or 80-20 percentage basis. And there is this recent survey by Kaggle, a pretty big survey actually, that came up with logistic regression on top, showing that about 2/3 of people in industry use logistic regression today as the leading model for machine learning. And neural networks are, of course, high, but there is still a way to go for them to catch up. So for these reasons, we choose to work with and accelerate generalized linear models. So what is Snap Machine Learning in the end? It is basically a new framework for training fast, generalized linear models. And generalized linear models, as you see here, are basically a subset of what we call machine learning. Deep learning is another subset, and these two are disjoint. So where do we fit in the ecosystem of existing libraries? There are very popular libraries like scikit-learn, Python scikit-learn today. Others like Apache, Sparc, MLlib, which is the machine learning framework in Sparc. There is TensorFlow, which came up top before in your preferences. And here we are. And SnapML tries to cover, to be, if you want, complementary, and try to cover some of the, I wouldn't call it weaknesses, but the choices, the design choices of other libraries. For example, scikit-learn today is very broad. It covers a multitude of machine learning models and a little bit of deep learning models. However, it doesn't do GPU acceleration. It doesn't offer distributed training across multiple machines, which is necessary when you have big data sets. And only recently started supporting sparse data sets. And TensorFlow, on the other hand, pretty much covers everything, but as we will see later, is not so well suited for sparse data structures, and is not so well suited, for this reason, for machine learning, although it is perfectly suited for deep learning. So SnapML tries to do a little bit of everything. It offers GPU acceleration, it offers distributed training, and supports sparse data structures. On the other hand, it offers only a subset of the possible machine learning models today. So I will go in a little bit more into the details of the architecture. Why is this? Why can we achieve fast training? Why can we achieve scalability? One of the main reasons is that in SnapML, the biggest design choice has been to not design an algorithm and a system, but to, when to design the algorithm, be very aware of the system on which the algorithm will run, and therefore make the algorithm adaptive to the system characteristics. And one of the dimensions here is the parallelism that today in modern systems is offered at different levels. So on the first level, it is offered at the cluster. So you have multiple workers, say multiple servers, connected through a network. Then if you zoom in a particular server, you have possibly, today actually you have multiple cores, multiple CPUs, multiple sockets even. And then potentially also, and this is actually very much happening today, you have accelerators, accelerator units on the server itself. For example, GPUs, maybe FPGAs. Now, if you zoom in one level down, on the GPU or on the FPGA or on the TPU, the tensor processing unit of Google, you have another level of parallelism. There you have thousands of cores, smaller cores, but yet which can be exploited to give you a big level of parallelism at this level. Now, however, not all of these units, not all of these computer units are created equal. They have very different compute power. For example, comparing the GPU with a core of the CPU, we have different compute powers. They have different memory sizes. The biggest memory size on a GPU today is 32 gigabytes, whereas we have terabytes when we go to this level, to the server level. We have different bandwidths of communication. For example, if you look here, the network, today we're having networks in the order of 10 gigabits per second, maybe 100 gigabits per second. However, when we look inside a server, the communication bandwidth between the CPU and the GPU is typically more than 100 gigabytes per second, or in the order of tens of gigabytes per second. And the same goes for CPU to CPU. So therefore, you cannot design an algorithm that goes and, say, for a large data set, spreads your data across and agnostically to the system communicates the same between whether it is at this level or at this level or at this level. And this is actually the design philosophy of SnapML. So as I was saying before, what do we do typically when we have a large data set? We have a data parallel framework, and that's what we choose to do here in SnapML also. We take the data set and we partition it across, for example, the cluster. Because the data set may be so large that it doesn't fit in the memory of a single server. Maybe the server has a memory of 1 terabyte, and we have a multi-terabyte data set. So therefore, we spread it across, we partition it across the nodes in a cluster, and furthermore, in a further level down, we partition it across the accelerator units that are potentially present. So this is called the data parallel framework. Now, what can we say about communication? Which is necessary, because now we have a model to train, and we need to cross boundaries, either at this level, so either at the network level between nodes, or at this level within a server. So as we said before, here we have gigabits per second. Here we have tens of gigabytes per second. So here we have low bandwidth and high bandwidth, and we need to design our algorithm to take advantage of the differences in this bandwidth. So this is what we do here actually in SnapML, and this is, again, another fundamental building block. We apply a state-of-the-art framework in order to do distributed learning. It's called Cocoa. It has been recently proposed. And actually, we apply it in a recursive manner. So what we do is, if you look at this picture here, actually, is we take two, say, communication rounds, because machine learning algorithms, let me just pause for a second. Machine learning algorithms are iterative algorithms. What that means is that you do a little bit of computation, and then you update the model based on this computation. For example, you change the gradients, then you update your model, and then if every other worker does the same, the model has now changed. But every worker is not aware of the changes that other workers have made to the model. Therefore, there has to be a round where all these updates are brought together, say in a master node, aggregated, and then communicated, broadcast back to the workers so that they continue their work updating the new now model. Now, intuitively, if you don't communicate very often, and you just, every worker keeps updating the model and all the time, and never communicates, you actually end up in a situation where your model is stale. So you train very well based on your local data, so worker 1 and worker 2. The worker 1 trains on its local data, and worker 2 the same, but they never handshake, they never communicate, so the model that they have trained two separate models, but not a global model that is good for both data sets, both parts of the data. So the less you communicate, the more difficult it is to converge to a good model. So the less your accuracy is, and it stagnates to a low level. On the other hand, if you communicate very often, so say you do one iteration on each model, and every iteration, then you go back to and accumulate the model, and then broadcast back. That means now that you have a lot of time spent in communication. So if you're in a scenario where your communication bandwidth is not very high, for example, across the network, or across a data center, or across data centers, then your convergence time will suffer because it will be dominated by communication. So there's a clear trade-off between doing more computation locally and doing more communication across workers. And this is what we try to tackle here. We try to offer, basically to offer parameters that exploit different parts of this trade-off depending on the system on which your machine learning algorithm is running. So what you see here schematically is that between two communication rounds, this is the nth communication round, this is the next one, you have multiple rounds of training in, let's say, the GPU. You have n training rounds here, and also communication rounds between now the GPUs. And now let's not forget that this communication is very cheap. We're talking about the communication now within a server. The GPU to GPU bandwidth, or the GPU to CPU bandwidth, is, as we said, tens of gigabytes per second. So you can afford to do many rounds here. And after you have reached a certain level of, say, accuracy, then there is the time for all of these, say, local workers to go back and communicate so that they can synchronize their models. And then the next iteration, the next epoch, you do the same thing. And the key here is that you can adjust the amount of local computation according to the communication cost. So this is what, in the end, brings performance gains, and this is what, in the end, makes your algorithm adaptive to the system characteristics. Another element, which does not only have to do with distributed learning, but can also be applied when you do learning on a single server, is GPU acceleration. So, of course, you all know about deep learning, leveraging GPUs. Today, the prominent algorithm that is used to train neural networks is stochastic gradient descent, and is an algorithm that actually parallelizes very well on a GPU, because it boils down to matrix-matrix or matrix-vector multiplications. And GPUs are expert on these things. However, in linear machine learning models that we deal with here, the situation is not the same. There are other algorithms that have been shown to work better, to converge better than stochastic gradient descent for linear models. For example, stochastic coordinate descent. Stochastic coordinate descent, think of it as if you have a data matrix which has examples as rows and features as columns, operates at a single column at a time. So it takes one feature at a time and trains that feature only. So it is not very well known, it has not actually been shown yet how to do effective parallelization of stochastic coordinate descent on a GPU. So people have actually shown how to do asynchronous variants of stochastic coordinate descent on multi-core CPUs, but so as far as we know, we were among the first ones to do it on a GPU. And this has to do with ways to not really leveraging matrix vector multiplications, but coming up with new ways to do simple inner products of vectors in the GPU effectively. So that's yet another element that brings significant performance boost. And the third element is what we call out-of-core learning. Now, out-of-core learning is needed when the data does not fit in the memory of your server. So actually, when the data does not fit in the memory of your accelerator. So if you have a GPU or multiple GPUs, and you want to train based on the data that fits in the memory of your GPU. However, as we said, this memory is very limited, up to 32 gigabytes today in a modern GPU. So what do? The simplest thing to do is to transfer data from the CPU memory to the GPU memory in chunks. So you transfer one chunk, train on that chunk, and then when you're done, you transfer the next chunk, and so on and so forth. However, this is a very slow process, and it can be accelerated. There are different ways to accelerate that. One that we chose here and we came up with is something that is very specific to linear models. And basically what happens is that you are in your main memory, and during the time that the GPU is running and training, your CPU is examining the data in the main memory, is examining some form of gradients of the data in the main memory, and deciding which batch to bring to the GPU next. So it doesn't just bring any random batch of data to the GPU. It brings this batch of data that will actually maximize a certain performance indicator, which we call duality gap. In any case, it has to do with linear models. It's a detail here, but there are performance guarantees that basically say that if you are able to optimize this, say, duality gap, then your convergence is optimal. So by identifying the best set of data to load to the GPU, then basically your performance becomes faster, you run faster, not only because you load the data that has the most, say, information at a time, but also during time, the number of important vectors that you load to the GPU decreases. So this is shown here. If you see, this is the number of rounds, communication rounds, and this is the number of data that you transfer. So this is this algorithm that we came up with, and this is, say, sequential or random approaches. Random means that every time I pick, I don't know, 32 gigabytes of random numbers, random data, and push it to the GPU. Sequential means instead of random, I just push sequentially the data to the GPU. As you see, if you do that, you always send to the GPU the same amount of data all the time. However, here, if you do it in a smart way, after a few rounds, for particular models, you actually end up swapping only very few data points to the GPU. That's one thing that gives you a very big performance boost. And another one, as we said, is that these data are actually the important data that will lead to the maximal improvement on your model. And that is shown here, actually. This is the convergence rate as a function of time, and you see that you gain about an order of magnitude in the end in convergence if you do that. Now, this works very well with sparse models. So models like L1, lasso regression, and SVM, support vector machines. However, it doesn't work so well. It still works, but it doesn't work as well with other models. For example, logistic regression with L2 regularization, and so on. So for this, in this case, you can do something else. And you can actually design a streaming pipeline. As we said, the difference here is that when you are pushing one batch to the GPU is still working. What you want to do is that you want to hide the communication time, so the time that is needed to transfer this chunk of data to the GPU, behind the computation time of the GPU. So while the GPU is computing, you want to push the next batch of the data to the GPU from the CPU. And this we can do with using CUDA streams. And basically, it turns out that this streaming pipeline works quite well for linear models in particular. So this is basically the architecture. These are the elements that give us the big performance gains. Here I have a slide that shows what are the different APIs that we have today in this library. So we have a C++ CUDA template library that gives us the high performance. This is basically the core. And around it, we have different APIs. So we have an API, we call it local. This is designed for data that can fit in the memory of a single server. But it can also support multiple GPUs if they are available. As you will see later in a snippet, it is very much scikit-learn compatible. It almost looks and feels like scikit-learn. We have an Mpi API for people that do HPC and are used to that, and also a Sparc API. And these two are designed to work with larger data sets. So this is an example of the local API. This is a snippet of code. For people that are familiar with scikit-learn, I hope that some people here are familiar with scikit-learn, Python. Here we show an example of how to do logistic regression in SnapML versus scikit-learn. The top two lines are basically loading the data set and also splitting it in a train and test split. And then these middle lines will do either use the scikit-learn library here or the SnapML library. And they will invoke logistic regression as the model. So this is where you do the model building. And this is the only two lines of code that change. Everything else then is the same again. So you do the training, then you do the inference, and you can evaluate the loss of your model. As you see, the preparation, data preparation, and training is the same, exactly the same. The only thing that changes is that you invoke a different classifier from one library versus the other. So it's very much look and feel like scikit-learn. Another example, the Mpi example, is very similar in philosophy. So we describe the application again using high-level Python code. A peculiarity here is that actually these are all optional parameters, but there are some peculiarities, like, for example, which GPUs you want to use. If you have a server with 4 GPUs, you may want to use certain GPUs. And then you basically invoke an MPI run, and you can use that to launch this logistic regression application of 4 nodes with 4 GPUs per node in this case. And finally, the Sparc API. Again, this very much looks and feels like PySpark. It's again Python, high-level Python code, and you launch an application using Spark Submit. So the APIs have been designed so that they are very much consumable and very much adapted to what people are used to do today. However, the user will get a significant acceleration typically by doing this small change in the code. So just a little bit of experimental results, hoping there is some time. Yeah. OK, so I just chose to show you some experimental results from, I think, an application that everybody here knows and understands. This is called click-through rate prediction. This is basically the business of many of the internet giants today. As you know, every time you visit a search engine, you're hit by all these advertisements. And these advertisements are actually personalized to you and your previous searches. Maybe your geography, where you are currently, and so on and so forth. And there is huge engines running underneath, big models, machine learning models that are being trained in order to do that. So the question is, can we train a machine learning model to predict whether a user will click on an ad or not, that is given to him or not? Now, big internet companies make big money out of this, and they want to make sure that they maximize the probability that you will click on an ad by placing it on certain parts of the screen, by your history, geography, and all kinds of other features. So you have a bunch of features. You have a label, say, when you train on historical data. The label says whether the user clicked or didn't click in this data. And you want to train a model that will learn the probability of click or no click. There is a company called Criteo Labs in France that has donated a very big data set, actually, which is publicly available. It consists of 4.2 billion examples and 1 million features. And a smaller version of this has actually been used in a Criteo Kaggle competition in 2014. It's only 45 million examples. And as you can see, I will use this data set to show you how the training is done in SnapML in one machine, one server, because here we have 40 gigabytes. We can fit in the memory of a single machine. And this data set clearly is 3 terabytes in SVM Lite format. It doesn't fit in a single machine. We will see how this performs in distributed training. OK, so this is the single node performance. We have the smaller data set. We use a single NVIDIA V100 GPU. And here we compare the performance of scikit-learn. This is logistic regression, by the way. This is log loss, so lower is better, and time in seconds. You see here the performance of the scikit-learn logistic regression. It takes about, 200 seconds to converge. This is TensorFlow, the same hardware used for all. This is TensorFlow logistic regression. It takes about an order of magnitude more. And this is SnapML. And it takes, as you see, about an order of magnitude less. So it's really fast in order to train certain types of linear models, in particular sparse models, as this one. And now let's see how it performs on very large data sets. As we said, here we use the whole 4.2 billion example data set. We train in 4 servers with 16 GPUs. Here we compare SnapML. This is, again, log loss. Lower is better. Training time in minutes. We compare SnapML using the 16 GPUs with TensorFlow, again, on the same hardware. We get about 3 orders of magnitude difference. And actually, because this is a very well-known data set, it's probably among the biggest publicly available data sets. There are many other instantiations of benchmarks that people have done in the recent past. One has been done in the Google Cloud using TensorFlow, using 89 machines. So compare now here 89 machines. Here we use 16 GPUs. We get about 2 orders of magnitude. And here, this is, again, TensorFlow on Sparc. This is by Criteo Labs themselves. And of course, accuracy here plays a big role. You can imagine there are blogs that say that, even from Microsoft, actually, that say that even a 0.1% increase in accuracy translates to hundreds of millions of dollars in revenue. So therefore, going lower is better here. And actually, being able to do the training faster is also important, at least for these companies. OK, so I want to finish with this slide. Clearly, as I said before, our goal was to create a library for training a particular set of models, at least initially, because we want to expand the library, actually, to train also other models, like random forests, like decision trees, even gradient boosting machines, which, however, is a different story. So when we went through this exercise, through training linear models, we understood a few things. So we understood that when you want to accelerate a machine learning algorithm, it's not important to look at the system only or at the algorithm only. You have to look at both of them. Today's mostly the libraries that train machine learning models are not executed efficiently on modern hardware. At least that's what we feel. And this is because what we said before, that these algorithms are stochastic in nature, highly stochastic, and they require communication after doing some computation locally. Now, more computation means better convergence. More computation, better local convergence, but you need to communicate across workers in order to reach convergence of your model to a global, say, optimum. So, but when you do communication, then the time to reach a certain accuracy suffers, because typically you go through some finite bandwidth. So therefore, what can you do? First of all, if possible, today in typical systems, you have multiple levels of hierarchy, you have different memories of different bandwidth, of different capacity. So exploit as much as possible the compute parallelism there, and exploit as much as possible the difference in the memory bandwidth. And then, as we at least tried here, is try and systematically partition your workload according to the architecture of the system. So if you have a system that consists of multiple nodes, which are even geographically separate, and then each node has multiple accelerators, typically the bandwidth within your node is much higher than the bandwidth across nodes. So therefore, try to do much more computation locally and communicate less often on the higher level, and so that you end up with better convergence faster. So, and actually this concept can be extended. We saw 3 levels of communication and hierarchy here, but you can imagine that it can be extended to other levels, for example, across data centers or across racks. And another very important thing is to be able to design algorithms that have parameters which can make them adaptable to the characteristics of the system. And these parameters typically need to be tuned. So tuning of these parameters so that they better fit to the underlying hardware is extremely important in order to get good performance. So nothing comes for free. I think that's where I want to end today, and ready to take questions. Thank you.
Well, Evkaristo. We had a few questions. I don't know how much we are on time, because we are almost quite over. But I mean, if we can bring up the Slido questions, maybe we can find some that we can answer quickly. Let's say we do 2 questions, and people can go out, and we don't feel bad if they do, in case you want to go for food. If you go for food, I want you to be back here at like 1 o'clock, because there's going to be a presentation by Coder Dojo Wien, which is like an interesting one. And the main concept starts at 1:15 again. Again, there's food here, and there's also food downstairs. So don't grab each other's plates and don't fight over the food. There's enough for everybody. So does SnapML only work on IBM infrastructure? And there's a more detailed one further down in the question as well, where they actually ask the architecture. But basically, that's the main question.
I can answer anything. OK.
Well, just answer that one and say like.
So today, SnapML runs on both Intel and Power infrastructure. It's being offered for free today from IBM. You can download it for free from IBM. As I said, it runs equally well on both types of infrastructure. It's being offered, let's say, a version of SnapML with support for customers is being offered to customers only on the Power infrastructure, but if you are a user, you can use it soon also on any type of infrastructure.
Which is the follow-up question, is it open source or is it just free at the moment?
It is just free at the moment, but there is discussions to make it open source.
Cool. That's a good one. Why GLM on big data? Isn't a great benefit of big data be able to train more complex models using deep learning? For shallow models, less data is OK?
Typically, this is true. However, when you have a lot of data, really, really big data, we're talking about, say, terabytes of data or more, it is very difficult to train very complex models. It is very time-consuming, And typically, you need to do a lot of tuning, actually mostly tuning, because there are many hyperparameters to tune in neural networks, GLMs, and things like that. So if you can afford to do that, because you have the infrastructure, because you have the time, then that's probably fine to train more complex models. You probably will get better accuracy, actually. But if not, and you're, say, time limited or budget limited, then linear models offer a very good alternative, and is actually the first stop of any data scientist. It typically establishes a very good benchmark.
Cool. Can the algorithm learn itself how to tune the cycles of distributed work and communication? It's an interesting one.
Yes,
so you actually do the training on the system itself.
That's an amazing question, by the way. And it is actually one of our next steps. And thank you for asking that. It is actually a very interesting question, and we're working on that. We don't know exactly how to do it yet, but I'm pretty sure there is a lot of interesting research there.
Well, in case the person who asked the question is looking for a job, I'm quite sure IBM will be interested. Microsoft too. So are there any more general limitations on the hardware and software, or is it possible to benefit from the parallelism in home office small node networks as well?
As far as I know, there are no general limitations to hardware and software. So today we're running on all kinds of Linux OSs. And I believe it is possible to benefit in all kinds of networks. We haven't tested every possible configuration, of course, but to our knowledge, we made the system, the framework, adaptive to the infrastructure.
Excellent. Thank you very much, Harris. If there's any questions, you probably will be around for people as well.
Sure.
And now let's get some food and see you back at 1. Thank you.
Thank you.